All right, so today we're going to be starting at least chapter 9, which is the last chapter in our course. This chapter is our look at confidence intervals, which we haven't done yet. We'll be seeing this more in stats decision making, of course, but here we're introducing the idea that sometimes instead of coming up with a single value for our estimate, for example, if you're looking at the population mean and you come up with a value of, let's say, 30 for X bar, that's a very useful piece of information, but sometimes it's not enough. It's also helpful if we have some sense of how much uncertainty there is associated with that estimate X bar. And so that's what this is all about. Confidence intervals give us an opportunity to provide not just estimates of a population value like the mean, but also assign a probability to the likelihood that the true population mean actually has a specific value. So we're going to start out by focusing on the population mean. Later on, we'll look at other cases. But right now, what we're trying to do here is construct basically a range of values within which we are highly confident that the population mean actually falls. So just a quick, simple example. What if we constructed a 95% confidence interval for the mean price of a gallon of gas in the United States, and we came up with this interval you're seeing here, $2.99 up to $3.39. So both of these are part of our interval. Think of this as the lower limit, okay, of our interval. And this is the upper limit. And so what this is saying is that we believe there's a 95% chance that the actual population mean is somewhere between 299 and 339. Which means that it also implies that the mean, the estimated mean X bar is halfway in between. Okay, so in other words, that would be in this case 3.19. You can tell because this number is actually $3.19 minus 20 cents. And this number is $3.19 plus 20 cents. This is how it was constructed. What we've done is we've taken the sample mean, and we've added and subtracted this 20 cents, which we'll see in a few minutes, is referred to as the margin of error. Okay, that's again how much uncertainty there is associated with this estimate of 319. Think of this as the margin of error. Okay, so not only do we know the average price in our sample of 319, but we have a very clear idea of how much variation there's likely to be from one gas station to the next. Okay, so what that really is telling us is that the price isn't that much different among different gas stations in the US. I mean, if it had been, let's say, $1 up to $5, that would have been a different matter altogether. But here we can see that the average is 319. And with the 20% margin of error, we come up with our interval of 299 to 339. And so we're highly confident that the true mean is in that interval somewhere. Now, we still don't know that for a fact. It's still possible that it's a little higher than 339 or a little lower than 299, but the probability of that happening is extremely small. So, and again, so the lower limit is the 299. The upper limit is the 339. So this is a typical confidence interval that we will construct for a population mean. All right, well, here's another good example, something you've encountered on a regular basis. You want to determine the average length of time that it gets to get for you to get to school every day. So let's just say that you write it down and for a month, and it turns out that your sample of that month has a mean of 30 minutes. Okay, in other words, you keep track of your commuting time every day for a month, and that represents a sample because it's not the entire year. And you discovered that the sample mean is 30 minutes, but of course, you know that some days it takes less than 30 minutes if the traffic is good, or it might take more than 30 minutes if the traffic is bad. A lot of things can happen to affect your commuting time. Some days you just drive faster. Some days you're just focused on something else and you're driving slowly. Who knows? But on average, it will be 30 minutes. The question is, what is the range of possible values for commuting time? For example, are we getting there within a couple of minutes of 30 minutes every single day, or can the variation be as much as 5 or 10 minutes on either side? So what if we discover that our interval is 25 up to 35? Given that the sample mean is 30, that means you've got here 30 minus 5, and here you have 30 plus 5. So of course, X bar is the 30, which implies that the 5 is the so-called margin of error. And what that means is that we're 95% confident that the actual time is between 25 and 35 minutes. You can also think of it as very rarely will it take less than 25 minutes or more than 35 minutes. Once in a while it might, but it's very unusual. Now, by the way, how do you know that it's 95%? Well, we choose this up front, and that will actually help determine the size of this margin of error. We could also, in principle, construct our confidence intervals, let's say at the 90% level of confidence, or sometimes we could do 99. Those are the three most popular choices, by the way, 90, 95, and 99. Theoretically, we could do anything we want. We could have 97 or 92, but most of the time, we end up choosing 90, 95, or 99, depending on how accurate we need this thing to be. So, by the way, here's an interesting point of terminology. The 30 minutes that we're used to seeing for our X bar is sometimes called a point estimate. The point refers to the fact that it is a single number. The fact that it's an estimate because we don't know what the true population mean really is. So this is an estimate. 30 minutes is our estimate, but the word point is used to describe the fact that this is a single number. Well, if that's the case, the entire interval itself would be referred to as an interval estimate, because it's clearly an interval and it's also an estimate. We don't know what the population mean is, but we do have some idea what it might be because of the way we've constructed this interval. So all the other things being equal, having the entire interval is more useful information, but it obviously takes more time and effort to calculate it as opposed to simply calculating the sample mean. For some applications, that's all we need is the sample mean, but for other cases, we really do need this interval. Okay, now it turns out that for the first time in this chapter, we'll find cases where we're not using the normal distribution. We'll also not be using the binomial or the Poisson. So in other words, we're going to be introducing a brand new continuous probability distribution in this chapter because we're going to need it. Now, it's not that difficult to learn it. Well, there is a separate table for this new distribution, but also your calculators have it built in there. Now, I have this wonderful simulated TI-84 here. I don't remember if I mentioned this before, but you can get this yourself by going to this website. If you need this for some reason, it's free. Texas Instruments is making it available to us. But you have to be a little careful. You need to correctly type in this website. If you make any typos, you're not going to get what you're looking for. So let me just put this in here so you can see it better. Well, I don't know what that's all about. All of a sudden, I seem to have upset Word. Well, I don't know what that was all about. Oh, for God's sake. Yep. What a shocker. Technology is failing me. All right. All I wanted to do was copy this link. Okay. Apparently, that's not allowed. All right. So why don't we do this? Let me type it. TI89.com/online-calculators. You notice I'm capitalizing them. /TI84-online PHP. Now it's very particular. Don't type it exactly right. you'll have problems. So let me make this bigger for you. There we go. It's all one line. Now, don't fool with it. Just type exactly what you're seeing there. And when you do, oh, let me put it back on so you can actually copy the thing. This is what it looks like. And if you type that, there's a link you need to turn on so that it knows what you want to do. I don't know how long this thing has been available. I discovered it 100% by accident last week or the week before. It's probably been there for a long time and I just didn't realize it. But the advantage of this is that I can show you on the screen exactly what I'm doing with my calculator. So once you, and again, I've discovered from experience that these, whenever you see a capital, make sure it really is a capital. It seems to matter. Anyway, once you've done that, it'll bring you here. And then you got to scroll around a little bit. You're looking for the link. There it is, testnav.com. And then it gets a little strange. Don't know why, but just hit start twice, and then this little tiny icon here is meant to represent the TI-84CE. So we click that on, and there it is. Now, when you're using this thing, you've got to be careful with it because you might think that you can type on your keyboard and get everything you need. And sometimes that's true, and sometimes it's not. In order to be on the safe side, your best bet is probably to choose the keys and then click on them with your mouse. All right, you try to type, sometimes it works, sometimes it doesn't. It's particularly finicky about this negative key right here. You must click this button with your mouse. Don't use your keyboard for that one. It will not work. So aside from all of that, it does work just like the CE, the TI-84CE, and the TI-84 itself too. Just pay attention to what you're doing. Anyway, so now with that being said, the distribution that will be, this brand new distribution that I've been hinting at is built into this calculator. So you could theoretically use a table, and I'll show you how to do that, but it won't prove to be necessary. Anyway, a little more terminology here. We've already seen what we mean by a point estimate. A single value, which is an estimate of a population parameter. Here, 30 minutes. The interval estimate is the corresponding sample, confidence interval. But we also define the word point estimator, very subtle difference, to be the formula that is used to estimate these population parameters. So in other words, what they're saying here is that the formula for X bar, because it is giving us an estimated value for the population mean, this formula is called a point estimator. But the actual value that you come up with from your data is called a point estimate. Okay, or the suffix or like that indicates it's a formula. Estimate, the ending TE, means this is the numerical value that you came up with. It is unique to that particular set of data. It will be different every time you apply the point estimator. And then equivalently, an interval estimate is that confidence interval that we saw earlier. Let's say we were using the example of 25 to 35. The interval estimator is the formula that's used to come up with these two numbers. Okay, so it's actually a little bit messier than it looks at first glance. And we'll discuss it in a few minutes, but Estimate is the numbers that you got. And estimator is the formula you applied to come up with these numbers. All right, now, just another quick example. If we determine that our interval is 5 to 10, that means that the probability that the population mean is somewhere in that range is about 95%, and that is our interval estimate. Now, here's an important detail. How do you know whether to use 90, 95, or 99%? Why would you choose one over the others? Well, here's the whole idea. In order to have the highest level of confidence, this one is the widest, or includes the most value. Let's say that we're using that example before from your commuting time, and we came up with 25 to 35. In order to bump that up to 99, we have to include more values. And you might end up with 22 to 38. Because what's happening is in the 95% case, you're describing your experience 95% of the time. The 99% confidence interval includes some extreme cases, some of the days when there was nobody on the road and some days when there was tons of traffic. So what happens is, in order to have the highest level of confidence, we must have the widest interval, which indicates the greatest degree of uncertainty. And by the way, this means that the margin of error, instead of being 5, is 8. Because here, remember, it was 5. And then let's say here, we have 27 up to 33. And that the margin of error is only 3. Because we're allowing for a 10% chance that our population mean is not in there anywhere. Okay, so we'll discuss this again as we go along, but I just want to mention that before we go any further. The choices of our confidence level, as it's called, will depend on how much uncertainty we're willing to tolerate. Okay, so to be really sure, like with a 99% confidence interval, you must have a huge margin of error and therefore a wide range of possible values. Okay, so in general, a confidence interval is constructed by simply taking a point estimate such as X bar and then adding and subtracting what we will call our margin of error. Okay, we've already discussed the margin of error. This is the measure of uncertainty. This is the symbol for plus and minus. And that means you're going to wind up with point estimate minus the margin of error as your lower limit. And then your upper limit will be the point estimate plus the margin of error. So now that raises an interesting question. It should be pretty clear that when we're dealing with the population mean, that the point estimate is clearly X bar. There's no question about that. The margin of error is the tricky part. How do we come up with this number? What is it based on? Well, it depends. It depends on several factors. Okay, but ultimately it comes out that there's only 2 or 3 basic possible cases that we can encounter. Ultimately, the decision here comes down to whether or not the population standard deviation is known to us. Okay. Yeah, the population standard deviation is a huge deal because if you don't know what it is, you have to use S, the sample standard deviation, to estimate it, and that increases the uncertainty associated with our results. So, case one that you're familiar with, if sigma is known to us, we're going to use the standard normal distribution to construct our confidence interval. And of course, we already know how that works from the previous 2 chapters. We're actually pretty good at this now. But if not, that's when the mystery distribution gets involved, the one we haven't been introduced to yet. We'll save that discussion for later. Right now, let's focus our attention on what happens if we do in fact know the population standard deviation. So here's what it looks like. So you'll see now, this entire expression, which we'll have to explain in a second, is the margin of error. And of course, X bar, we know what that is. That's our point estimate. Whatever that number is the estimate. And that's our margin of error. Now, you already know what sigma is. Sigma, of course, is the population standard deviation. N is, of course, the sample size. What is this? Oh my God. Now that's something new. Clearly, it has something to do with the standard normal distribution, but there's that subscript here. What is this? Well, this is the Greek letter alpha. And then you see that we're going to divide that by 2. So what does this thing mean? All right, well, first things first. Z alpha over 2 is a z-score. It's taken from the standard normal distribution. The alpha over 2 tells us where it's located. And because of the symmetry of the normal distribution, there's going to be 2 of these, one positive and one negative. So for example, we could have Z alpha over 2 here. And the negative would be here. What does it mean? It means the area in this right tail is alpha over 2. And this area in the left tail is also, because of the symmetry of this distribution, alpha over 2. Now that still leaves open the question, what is alpha? Well, alpha is known as the level of significance, but what does it mean? Well, this is related to the confidence level. All right. How is that? So let me show you how this works. How is that related to our confidence level? So we're going to define the following terms. First of all, 1 minus alpha is known as the confidence coefficient. Now, by the way, I want to point out before we go any further, alpha is bounded between 0 and 1. If I multiply this by 100, it is now known as the confidence level. So confidence coefficient, confidence level. So let's just say that we're interested in constructing a 95% confidence level. Confidence interval at the 95% confidence level. In other words, it's the interval, we are constructing an interval, but it's the confidence level that determines how wide it is. And let's just say we pick 95%. So what this means then is that 100 times 1 minus a is 95. This is a 95% confidence interval. Now I'm going to algebraically divide both sides by 100. So 1 minus alpha is 0.95. 1 equals 95 plus alpha. That implies that this alpha is 0.025. 0.05. So in other words, for 95% confidence interval, the alpha is 5% or 0.05. We usually write it as 0.05, but of course it means the same thing. But when we go to the tables or the calculator, usually it's written as 0.05. So that's our alpha, which is also known as the level of significance. So what about the other two, the 95, the 90 and the 99% cases? All right, let's find it. Based on that logic, 99% confidence. Means that alpha is either 1% or 0.01. If you notice, these two have to add up to 100%. And for 90% confidence level, alpha is either 10% or 0.10. They have to add up to 1, 90 and 10. So what that means then is this. Let's go back to that graph. Let's say that we're looking to construct a 95% confidence interval. %5% or 5.05 is our alpha. So alpha over 2, of course, is therefore half of that. So when we draw this thing, the two z-scores will be here and here. This one contains 0.025% of the total area under this curve, and this one also does. Now, here's the big question. And by the way, we can now rewrite this as z alpha 0.025 and minus z 0.025, since we know what alpha is now. So what I need to do is find the z-score such that the area to the right of it is 0.025, or equivalently, the area to the left of it is 0.97. So in other words, let's take a look at just the right tail for a minute. I'm looking for this mysterious z-score. I have 2.5% in the right tail. Everything below that has an area of 0.975, since we know that they must add up to 1. Now, I can do one of two things. I can look it up in a table. What I need to do is look in the body of the table for 0.975. Let's do that right now. So look for 0.975. That's going to be, here it is. And that gives me 1.9. And then on the top, it's actually 0.06. There you go. You can see it now. So that means this z-score is 1.96. Or think of it this way. Probability that z is less or equal to 1.96 is 0.975. And you can confirm that on your calculator. Let's go back here. We've done this before. We need second vars, normal CDF number 2. And we want everything from negative infinity up to 1.96. Got to be careful with this thing. The mean is 0 and the standard deviation is 1, because this is the standard normal distribution. Hit enter. Oh, sorry, I have to be down and paste. It should be 97.5%. That means we must have done this correctly. Now, based on the symmetry of the distribution, that implies that the one down here in the left tail this is negative z alpha over 2, or negative z 0.025. This left tail area is 0.025. We can go figure it out ourselves, but we know from the symmetry of the distribution that this must equal negative 1.96. Now we can try, actually I can show it here, some room. Negative 1.96, the probability of being below that should be 0.025. Let's go prove it. All you have to do is change the sign. Let's go back second distribution, number 2, and change this to a negative. And let's see what happens. Oh, by the way, don't forget, I almost forgot, I almost blew it. You have to use this button for the negatives in this thing. Don't try to use your keyboard for the negatives. It just doesn't seem to work. .025. With rounding, it's .025. And that's exactly what we expected. They're both correct. So that means that whenever we have a 95% confidence interval like this with the standard normal distribution, then the two critical values, or z-scores as they're called, are going to be plus and minus 1.96. Now, by the way, that never changes. So and given that I told you that there's only 3 cases, you may want to start writing these down somewhere in case it comes in handy. In fact, I'm going to make you a little chart right now where we'll have, let's say, this always drives me crazy when the default to these tables is green. I don't know what person in the right mind wants a green table. This is what they stick us with. Now I got to search around for all white, which is what a normal person would want. There we go. All right. All right, so what I'm trying to do is fill in the rest of them. And we'd like to make the font a lot bigger. So for 95%, we just got through showing it would be plus and minus 1.96. Using the same approach, 90% would be plus and minus 1.645. And 99% would be plus and minus 2.576. You can go confirm this later on if you want on your calculator, but it would proceed along the same lines as what I just showed you for 95%. Now, it turns out that none of this was really necessary because the calculator has this other wonderful function that we could use. Let's go back and see what that's all about. Second vars. Look at this thing, INV norm, number 3. If I tell it that I want an area. Now remember, when we did this, the area in the left tail was 0.975. I'm going to ask it for that. Now, by the way, this is something that the TI-84 doesn't have. The tail area defaults to left. With this calculator, we can change it to center or right if that is more comfortable for you. I think for now, we'll stick with left, though, because that's what we're used to. And there it is. There's your 196. Oh, so I didn't have to go to the table. I was able to use this INV norm function. And INV norm stands for inverse of the normal distribution. So now for 90%, the right tail area would be 5%. The rest of the distribution would be 95. So I'm going to change this just so you can see that. INV norm is number 3. I'm going to ask it for not 975, but 95, because that corresponds to a 90% confidence interval. And let's see how it reacts to that. 1645, which is exactly what the table is telling us. Now for this one, 1% is split up between the two tails. So to get the positive z-score, I would need 0.995. Let's go back to number 3. Let's change this to 995. And let's see if it agrees with us. It's approximately 2.576. 2.576. What do you know? So that's what these are all about. These are the ones, this is what you need in your margin of error. Okay, so it's, yeah, that Z alpha over 2 term is the critical value or Z score that is going to be incorporated into your margin of error. There it is right there. The other two are fine. Those are right in the problem. This is the tricky part. So let's just put that down here to remind you what this is. Oh my God. So that looked pretty complicated. Oh, by the way, I just realized that I did actually sneak these into the slides here. These instructions for using INV norm to find the Z-scores for all 3 cases. They're actually right here. I didn't realize it. But that's okay. No time went to waste, that's for sure. It's good practice. Wow. So now we're going to do some problems. And what you'll see is that we can go through and plug in everything we have. The only thing that is the least bit challenging is this Z-score. And even then, you can see it's not that difficult. In other words, this whole formula, the only thing that we have to really take care of is the Z-score. Everything else is already in the problem. But in spite of that, you'll be happy to see when we get to that point, the calculator also has a shortcut formula for calculating confidence intervals for the population mean. But we have to be careful how we apply this formula. Okay, so that's what's coming next. So sadly, I have to go do something else right now. So I think we'll save this problem for the next section of this recording. And but for now, at least you have a taste for what's coming. And now, so we're going to fool around with this formula and see at least 2 different ways of solving for it. Once that's done, we're going to introduce the mystery distribution and then see what happens when the population standard deviation is not known. Okay, so we're going to have to take a bit of a detour and understand the properties of this mystery distribution, and then we can go ahead and see how to use it. So it'll be worth the wait, don't worry. The next part will be ready very, very soon. You know, I kind of hate to leave you here with a cliffhanger like this, but it has to be done. So you can watch this now, and of course you can always read ahead in the slides and see what's coming. And we'll go over this the next time that we meet, which is probably going to be tonight or tomorrow. All right, so I'll see you then.